Precalculus Lesson 16 is an introduction to exponential and logarithmic functions, beginning with exponential functions. This is from section 4.1 in the College Algebra textbook. We begin with a definition. A function of the form f of x equals b raised to the power of x, where b is a positive real number and b is not equal to 1, is called an exponential function with base b. We start by looking at the exponential function f of x equals 5 raised to the power of x that has base 5, noting that 5 is a positive real number and that 5 is not equal to 1. Then we have g of x equals 1/9 raised to the x, where again 1/9, while a fraction, is a positive real number, and 1/9 is not equal to 1. We could even have the exponential function with base pi, h of x equals pi raised to the x, noting that pi is a real number and pi is not equal to 1. Any of these exponential functions are what I would refer to as basic exponential functions, and we'll continue by graphing the basic exponential function f of x equals 4 raised to the x. The first thing I would do here is I would choose the 3 x coordinates for points on my graph of -1, 0, and 1, and it doesn't really matter which basic exponential function I'm graphing. I always like to start with these same 3 x values. From these x values, I would find the corresponding y values. So for example, if x equals -1, y would be 4 raised to the power of -1, or 1/4. If x equals 0, y would be 4 raised to the 0, which gives us 1. And if x equals 4, y would be 4 raised to the power. If x equals 1, y would be 4 raised to the power of 1, or 4. So let's plot these 3 points on our graph, -1, 1/4, 0, 1, and 1/4. We'll connect these 3 points with a nice smooth curve. Note as the curve heads towards the right, it very quickly heads upwards, approaching positive infinity. As the curve heads to the left, it quickly approaches that x-axis. Although it never quite touches the x-axis, it gets very close to the x-axis quickly. The domain of this function is all real numbers. The range would be all real numbers greater than 0. We have an asymptote of y equals 0, or the x-axis, and the point 0, 1 is on this graph. All 4 of these characteristics apply to the graph of any basic exponential function. And let's go on to graph f of x equals -4 raised to the -x plus 2, where we'll start with the graph of y equals 4 to the x that we just completed, and we'll use transformations. The first thing I see is 4 raised to the -x here, and I'm going to do a reflection of the graph of y equals 4 to the x about the y-axis to give me a graph of y equals 4 raised to the -x. From y equals 4 raised to the -x, I will reflect this graph about the x-axis for the graph of y equals -4 raised to the -x. And then last of all, I take y equals -4 raised to the -x, and adding 2 to the function means to graphically shift the graph up by 2 units. So here we have the graph of y equals f of x, or -4 raised to the -x plus 2. Note that in addition to the graph moving up by 2 units, the horizontal asymptote moves from y equals 0 up to y equals 2. So we have, for this function y equals f of x, a horizontal asymptote y equals 2. We also have a domain of -infinity to infinity, all real numbers. That hasn't changed. The range has changed slightly. Along with the asymptote, the range is now -infinity to 2. And one thing to note here is that when we're finding the horizontal asymptote of an exponential function, if you look at this number kind of stuck on the end here, that is going to give you your horizontal asymptote. If we're thinking of graphing, say, g of x equals say 5 raised to the power of x, note that you can imagine having plus 0 stuck on the end here, and then your horizontal asymptote would be y equals 0. Now to graph f of x equals 1/4 raised to the x. Again, we start with x coordinates of -1, 0, and 1. To determine the y coordinates here, I would first of all take 1/4 raised to the power of -1, which would give me 4. Then 1/4 raised to the 0 is equal to 1. 1/4 raised to the power of 1 would give us 1/4. And plotting these 3 points we have on our graph here, we connect with a nice smooth curve to get the graph of y equals f of x here. Note that the domain of this for this function is still all real numbers. The range is real numbers greater than 0. The asymptote is still y equals 0, the x-axis, and we have the point 0, 1 on this graph. This is a basic exponential function, just like y equals 4 to the x. The difference here is that as our graph approaches the left, it heads upwards towards positive infinity. As the graph approaches the right, it gets closer and closer to that x-axis. So the directions left and right have changed, but not much else. And then additionally, I'm going to note before we go on that if I superimpose the graph of y equals 4 to the x on here, note that we could have taken the graph of y equals 4 to the x, reflected that graph about the y-axis to give us the graph of y equals 1/4 raised to the x. Let's see why it works that way. Well, if I start with y equals 4 to the x, if I reflect about the y-axis, I have y equals 4 raised to the -x. And then that would be the same as y equals 4 raised to the -1 times x, or y equals 4 raised to the -1 raised to the power of x. This would be a good place to make a note to review powers of exponents if you're a bit rusty on those. And then finally we would have y equals 1/4 raised to the power of x. So indeed we did get the same graph by reflecting that graph of y equals 4 to the x about the y-axis. Now, the one-to-one property of exponential functions. If you review the graphs that we've been looking at here, you'll note that these graphs are graphs of one-to-one functions. So exponential functions are one-to-one functions, and we can use the one-to-one property of functions from a while back. For example, if we have f of m equals f of n, and f is a one-to-one function, then that tells me that m has to equal n. So that's where we get our one-to-one property of exponential functions, which says if b to the m equals b to the n, then m equals n. And so let's work through some examples here. First of all, we're going to solve the exponential equation 2 raised to the 4x equals 8 by getting the same base on each side of this equation. So on the left side, I have 2, base 2, raised to the power of 4x. On the right, I can easily rewrite 8 as 2 raised to the power of 3. Then the bases are the same, and I can, from there, assume that the exponents have to be the same. So I have 4x equals 3, and I solve to get x equals 3/4 as a solution to this equation. Now let's try solving 3 raised to the 7x equals 81 raised to the 4 minus 2x. We have 3 as a base on the left side. To get 3 as a base on the right side, I'm going to write 81 as 3 raised to the power of, let's see, we have 3, 9, 27, 81. 3 raised to the 4th power would give me 81. And then we still have 3 raised to the 4th power raised to the 4 minus 2x, from which we will simplify to write this as 3 raised to the 4 times 4 minus 2x, or we'd have 3 raised to the 7x equals 3 raised to the 16 minus 8x. Now the bases are the same, tells me the exponents have to be the same, so 7x equals 16 minus 8x. I add 8x to each side to get 15x equals 16, and finally divide through by 15 and find x equals 16 over 15 is a solution to our original equation. Now, 8 to the x equals 1 over 128. Since 128 is not a power of 8, I need to find a different base. And I'm going to go with a base 2 because I happen to know that if I cube 2, I get 8. And also, some power of 2 is going to be equal to 128. So to determine that power, I use my fingers, which you can't see right now, but I have 2, 4, 8, 16, 32, 64, 128. Using my fingers, I can tell that 128 is 2 raised to the 7th power. And so I now have 2 raised to the 3x equals 2 raised to the negative 7th, or 3x equals negative 7, from which I solve to get x equals negative 7/3 as a solution to this equation. Try on your own number 1. Solve the exponential equation. 5 raised to the 4 minus x equals 125.